Hey guys, this is Bharat and welcome to my channel. Today we're going to study one of the most interesting topics in computer vision, edge detection. This topic in particular is in research from the past 50 years and many researchers have suggested various algorithms to tackle this problem. John Canny is an American computer scientist and he had proposed an approach to edge detection in his paper of title A Variational Approach to Edge Detection. The algorithm he proposed is famously known as Canny Edge Detector. Now this Canny Edge Detector has 5 stages of implementation. The first stage is Gaussian filter. The functions which are top right corner of the slide are Gaussian functions in 1 and 2 dimensions. The first function is the Gaussian function in 1 dimension and the second function is the Gaussian function in 2 dimensions. The graph below shows the plot of these functions in 1 and 2 dimensions. The peakiness of the curve here is decided by the standard deviation sigma, which is in the function. Now when the value of sigma is low, the curve will look more peaky and while standard deviation is increasing, the curve gets flattened. Now, how does this Gaussian filter help us? By applying Gaussian filter, we can get rid of unwanted noise. Consider the image below, which is of name original. When we apply a Gaussian filter, that means when we convolve a Gaussian filter across the image, which is of size 5 x 5, which is or 3 x 3, as shown in the image, which is top left corner of the slide. With standard deviation 3, we should get a less blurred image. As we go on increase the standard deviation, the blurredness will be increased. So why we prefer Gaussian filters rather than mean filters? Well, Gaussian filter will preserve the edges more than the mean filters and average filters. Now let's move on to the next stage of implementation, applying Sobel filter. While Sobel filter or Sobel edge detection is used on prior to Canny Edge Detector. Basically, we will find the x and y derivatives of the image by convolving the image with these two filters gx and gy, and then we will find the magnitude at each and every pixel of the image and plot the image. After applying the Sobel filter, we will get an image which is as shown in the image below. The next step is finding the gradient matrix. The gradient matrix can be found by applying tan inverse gy by gx. Gy and gx are the derivatives in y and x directions at a particular pixel at each and every pixel of the image, and preserving these values and making an array out of it. After making a gradient matrix, we will be doing non-maximum suppression. Well, the name itself suggests that we are going to suppress non-maximum pixels in the image and produce sharp-edged images. Now, if the image is a straight line, the gradient will be perpendicular to it. Not straight line, every edge has its gradient perpendicular to it. So, if the angle of the gradient is in the region of this blue region, which is the image to the right, then we will be comparing the pixel intensities of a pixel under consideration. We will be comparing the pixels above and below of a pixel under consideration, and if the pixel under consideration has high intensity, we will be taking it and remaining pixels are suppressed because they are unwanted responses or they are non-effective responses. and then we will be converging to a fine, thin edged 1 pixel edge images. And the last but not the least step is applying double threshold method. Double threshold method is to get rid of unwanted edges but unwanted pixels which are not of edges. Basically, we have a weak edged pixels and strong edged pixels. Every weak edged pixels will be surrounded by one or two strong edged pixels. One or two or many strong edged pixels. But a weak pixel of noise will not be surrounded by any of the strong edged pixels. So we will exploit this phenomena to get to know which are which are pixels of edges and which are pixels of noise. So we will be finding two thresholds, a high threshold and low threshold, as shown in the code snippet below, and then if the pixel under consideration have intensity greater than the high threshold, we will consider the image. We will consider the pixel. If the pixel under consideration have intensity less than the low threshold, we will suppress the pixel. If the pixel under consideration have pixel intensity between high threshold and low threshold, then we will check if any of the pixels surrounding the pixel under consideration have its intensity greater than high threshold, then we will consider the pixel. If the pixel under consideration doesn't have any pixel surrounding it having intensity greater than high threshold, we will be suppressing it as it is a pixel caused due to noise. And finally, we will converge to a binary edged image of our original image. So I think it's a lot of theory completed now. Let's jump right into the code and know how to implement a Canny Edge Detector algorithm in Python. Hey guys, let's start the coding part. Let's import the required libraries for Canny Edge Detection. From SciPy, import ndImage for convolving and other important functions. Import image.io. Yes, image.io for reading the input image, and NumPy and Matplotlib pyplot for matrix and plotting operations. Import NumPy as np. Also import matplotlib.pyplot as plt. That's it. These are the required libraries. Now let's read the image using imread function of image.io library. First of all, I'm gonna show the image which you are trying to find the edges on. This is an image of a crater on the surface of the moon, which is in a grayscale, in a grayscale format, and we're gonna find edges on this image. Image.io.mread view the name, make sure that the image file is in the same directory as where your code is when your Python file is located, and just we're gonna convert this image file into int32 format. I'm gonna plot it by using a pyplot. So plt.mshow takes image and cmap, where we should specify whether it's a grayscale image or a color image. So get CMap, and we're gonna specify it as gray, and plt dot show will plot the image and show for us. Yeah, here's the image. Now the first stage of Canny Edge Detection is applying the Gaussian filter. We can apply the Gaussian filter by using ND image package, which has been imported from SciPy. So image, this can be done using ND image dot Gaussian filter function, which takes image and sigma as parameters. We take sigma as 1.4, which is a common attribute, and store this into image Gaussian variable. If there is a variable name image Gaussian. Yeah, done. Next we're gonna plot it again the same way which we have done earlier. Just copy it and paste it, and just change the name as Gaussian. Just see the image. Yeah, as you can see, the image here is a bit blurred because we have applied the Gaussian filter to get rid of unwanted noise. The next is applying the Sobel filter. For applying Sobel filter, we should have two functions here: a Sobel filter function, which we're gonna define, and a normalization function, which will be used further in our code. I'm gonna just copy the code from my repository, and I'm gonna paste here because typing this can be a time-consuming process. So, what are this Sobel filter function tells us? Sobel filter function takes image and direction as two inputs. When the direction is x, we will convolve this array with our image and get our x derivative and store it in s image variable and return the image. But if it is when the direction is y, then we will convolve our image with gy, which is this matrix, and then store it in a variable s image and return to it. And below it is a normalization function, which just normalizes our image. That means dividing each and every pixel in the image by the pixel which has high intensity. We're gonna just interpret it. Yeah, it's done. Now let's find the x and y derivatives of the image. Let gx be the x derivative, Sobel filter, and let's give image Gaussian and direction as x. Gonna normalize it again. Normalize. I think this is a function name, right? Yeah, normalize with giving gx as input. The same way we're gonna find derivative of gy, Sobel filter image Gaussian and y, and gy equal to normalize gy. We're gonna plot and see how these derivatives look like. As we done before, we're gonna use plt mshow function for this purpose and replace this image Gaussian with gx and gy. And let's see how this x and y derivatives look like. Oh, wait. Image Gaussian is not defined. Wait. It's a spelling mistake here. Yeah, now it will be good. Now we have got x and y derivatives here. We can find the magnitude using hypot function of MATLAB. Sorry, hypot function of NumPy. And let's see how magnitude of this image look like. And just change this name as mag. Yeah, this is how image look like after applying Sobol filter. Now the second stage of application of Canny Edge Detection is completed. Now let's start the start stage, that is finding the gradient matrix. G matrix equals to np dot decrease np dot, we can use arctan2, that is tan inverse gradient. Gradient means tan inverse of gy by gx, so we can use arctan2 we can give gy comma gx as inputs, and we can get a matrix of that gradients. Let's see how this matrix look like. See, this is how it look like. Now we can apply non-maximum suppression. For application of non-maximum suppression, we need a function for that. I'm gonna just copy and paste a function which I have already written for not wasting the time. And this is how the function look like. As I mentioned earlier, this function will loop through each and every pixel, and if the check the gradient direction, and if the direction is specific, if the gradient is specific direction, it will check whether the pixels above and below or any other direction is greater than or below, or greater than or less than our pixel under consideration. And if it is greater than, then we will take the pixel into consideration. If it is less, then we will just suppress the pixel. The same is happening with just these if conditions. We'll check whether in which space, in which portion does this gradient direction is in the entire space. That's it. In which portion does this gradient direction is in this entire space. As I said earlier, this is the image. This is the blue region here is minus 22.5 and minus 22.5, and this is also minus 157.5 and 157.5. This blue region. So if that gradient lies in this blue region, we will be comparing the pixel above and below with our pixel under consideration. If the pixel above and below have values greater than the pixel under consideration, we will will suppress our pixel under consideration. If the pixel above and below have values less than our pixel under consideration, we will consider our pixel under consideration, and we will suppress will consider our pixel under consideration. That's it. And that's how this function works. Now it's a lot of, I think it got clear to you. Now just find the image after non-maximum suppression. Let's just copy it, paste it. Sorry. Let's give image input as what is our magnitude. Find that mag and that is Gmat, right? Yeah, have suppressed the image. We're gonna normalize it again. Image NMS equals to normalize image NMS. Again, we're gonna plot it and see how this image look like after normalizing. Image NMS. Let's see what it look like. Okay, wait. Non-maxima is not just we should confirm interpreted before. So now it will run well. Yeah, this is how the image will be looking after non-maximum suppression. Before non-maximum suppression, the image is this. This has thick edges, and we don't need the edges like this. We need edges to be sharp and precise. And this is how the image look like after non-maximum suppression. But even then, we have the edges here which are not of a true edge. We have here edges due to noise. So we have to do double threshold hysteresis. We have to apply double threshold hysteresis method for getting rid of these unwanted fake edges. For applying double threshold hysteresis method, I have made a function for that. I'm gonna just copy and paste it for not wasting your time for typing it. And this is the function I have done. This ratios, high threshold ratio and low threshold ratio, will be decided by us. I'm gonna copy it in copy the image given to us in a variable gsoup, and we're gonna find height and width of that. Then we will get the maximum intensity of in the image and multiply it with high threshold ratio and get the high threshold. In the same way we get the low threshold. Now we will be looping into each and every pixel. If the pixel under consideration is having an intensity higher than the high threshold, we will mark the image as 1. We'll mark the pixel as 1. If the pixel under consideration having the intensity less than low threshold, we will just mark it as 0. And if the pixel under consideration having any surrounding pixels with threshold with intensity higher than the high threshold, then also we will be marking the image as 1. In this format, we're gonna convert our image into a binary image. Yeah, it's done. Let's see the final image. How this is the final image. Cool. Yeah, we're gonna give input as image NMS, image NMS. Yeah, let's plot it and see how the image look like. Final image, right? Yes. So this is how our final image will look like. This is the binary image, and as you can see, this edges are somewhat distorted. You can get fully attached edges by playing around with these two values. You can manipulate some things. You can increase or decrease it and see whether how it look like when you alter these values, and try it once again and see if it is improving or not. You can also see now I think the boundaries are well adjusted than before. By again playing increasing or decreasing values, we can get furthermore neat image. You can also play with the sigma value here, and that may also help you for some extent in getting a nice result. And that's it. And yeah, this is enough. The code of this project is uploaded to GitHub, and the link is provided in the description. And thank you very much for watching this content. I think you have liked it. I hope I will be making some more videos on machine learning image recognition, image processing, and more and more interesting topics in computer science and other fields. And if you like the content, please like, share, and subscribe to my channel. Bye.